Hello everyone, welcome to today's VisualCAM 2016 for SolidWorks webinar. My name is Anita Anand. I'm part of the sales team in MecSoft Corporation. Now our VisualCAM 2016 for SolidWorks is our CAM plugin that runs completely integrated with SolidWorks. It includes two modules that can be purchased and licensed separately, the mill module and the turn module. The mill module provides 2 through 5-axis machining functionality. It is ideal for the mold, die and tool, woodworking, rapid prototyping, and general machining. Our turn module is our module for programming 2-axis lathes. The new release, version 2016, was out this past Monday. So our main focus today will be to introduce the VisualCAM for SolidWorks suite of products. We will start with an introduction and overview of the functionality for the benefit of those of you who are new to this product. Next, we will highlight the new features of version 2016 for our old users, our VisualCAM for SolidWorks users. We have a lot of new functionality that you would be very excited about this year. Now on the panel today, I have with me Uday, our support manager. A lot of you have already met and spoken to him. He will be our presenter. We also have Don, of course, our support engineer, who will answer questions. And I believe a lot of you have spoken to Don as well. As always, some housekeeping before we get started here. Go ahead and use your chat window anytime during the hour to ask questions. Either Don, Uday, or I will try to answer them during the session. We will have a short Q&A after. If you're unable to get to any of your questions, we'll send you an email response after the presentation. So don't hesitate to put in any of your questions. We'll definitely get them answered. We are recording this webinar and we will make it available to you on our website. As soon as the webinar is done, I'll start doing the recording, and a couple of days you'll get an email with the location. Now, Uday, you ready to get going? Okay, let's start then.
Thank you, Anita. Good morning, good afternoon, good evening, folks. And thank you for joining us for today's webinar on VisualCAM 2016 for SolidWorks. Our VisualCAM 2016 for SolidWorks is a gold certified CAM product that runs fully integrated inside of SolidWorks and runs inside version SolidWorks 2010 all the way up to the latest SolidWorks 2016 release. This is available in both 64-bit and 32-bit platforms. Now, once you bring in a part into SolidWorks, you will notice that the VisualCAM plugin automatically appears in your part window. You will notice that the VisualCAM tab appears right in your command manager. You can switch between the mill and the turn modules. As we pointed out earlier, VisualCAM offers two modules. We have a module for milling and a module for turning, and you can switch between these two modules by selecting the appropriate buttons on the command manager. Now, VisualCAM's browser interface appears right next to your feature manager. You can toggle between your feature manager design tree and the VisualCAM browser by just a click of a button. The mill module offers 2 to 5-axis milling solutions with a wide range of toolpath methods in each of these, starting with 2-axis, 3-axis, 4-axis, and also simultaneous 5-axis methods. Our turn module offers 2-axis solutions for programming 2-axis CNC turning centers or lathes. Now, the part I currently have open in here is a prismatic part where there aren't any drafts or sculpted bottoms. Now, parts like these are ideal for programming using 2-axis, or also known as 2.5-axis methods. in 2 and 2.5 axis methods, the z remains constant as the cutter travels in x and y, and this is why it's typically called as 2-axis or 2.5 axis milling. Now the typical workflow here is on the program, on the machining browser, you have two main tabs, Program and Simulate, and you'd work your way left to right as you work through each of these groups under the Program tab. Now right under the Program tab, you have the Machining Objects browser, which allows you to manage your tools and machining regions. We have whole feature detection and knowledge bases, and we'll try to go over those features during this webinar today. Now a typical workflow here is in your Program tab, the first step is to establish your machine tool coordinate system. So you click on Machine, and in this process you can basically establish your orientation for machining. By default, the machining coordinate system is oriented in the same orientation as your world coordinate system that's established in SolidWorks. So if you need to reorient your coordinate system, you can use these controls in here to orient it. You can use either the spin angle, or you can pick a surface or a planar sketch to orient your coordinate system. Once you establish your machine tool coordinate system, the next tab over to the right is the machine tool definition, where you can establish the number of axes. For 2 and 3 axis milling, we would select 3 axis. For parts that require 4 and 5 axis machining, you can choose between 4 and 5 axis. Once you establish a machine tool setup, you would select OK, and this information automatically is updated under the machining job in your machining browser. Next, we would like to go ahead and select the post processor to use for outputting the G-code. VisualCAM includes over 225 different posts, which covers a wide range of CNC machines and controllers that are out there. So you could select the post from your list of post processors, and you could also specify your posted file extension, which is typically NC for most machine controllers, or if your machine controller expects a different extension, you can select it from the list, or you can even select Add New to add a new extension to it. The post processor that you select automatically also appears under the machining job. In the next step, we would like to create our stock geometry. So we will go down to the Stock tab and then click on Box Stock. Now in this process, the system automatically computes the stock dimensions based on the part that you model, and it automatically displays the length, width, and the height of the stock. Now for this particular part, I'm going to change the stock height to 2.5 inches and pick OK, and you will now notice that the stock is defined, and you can click on Show Stock Visibility to view the stock geometry that you just defined. In the next step, you would want to align the stock to the part, so we'll pick Align, and for the Z alignment, I would like to have the bottom face of the stock flushed with the bottom face of the part, so I'm going to pick bottom for the Z alignment and leave it at center for X and Y, and then select OK. Now the stock, bottom face of the stock is aligned to the bottom face of the part. In the next step, you could select the material you're going to be using to program this part. You can select it from the list of material types, and I'm going to use aluminum 6061 as the material, and then pick OK. And you can toggle the display of the material texture, and you'll notice that the texture of the material applies onto your stock block. So when you switch over to the Simulate tab, you'll notice that the stock transparency is set to opaque, and in the Program tab, it's more transparent, so you can view the part and the stock. And these transparencies can be set under preferences. In the next step, we would like to establish the work zero or the work origin. This is where you would typically set your XYZ origin for machining the part. So I'm going to go to work zero and choose set to stock. We'll pick higher Z and the southwest corner. And if you'd like to use this as your work offset as your G54, you can apply the G54 for your work offset number, and then you hit generate, and there's your work coordinate offset. Now saving your work in SolidWorks automatically saves all of the information that you programmed for this particular part. So which has the information of your stock, your work zero, and all of this information gets saved to the part. Now we have established the work zero or the program origin to the top face of the stock block and the southwest corner. Now we are ready to program some toolpaths in here. The first operation I'm going to do is a facing operation to face this stock blank to the height of the part. So we'll go over to the methods under 2-axis and we'll select facing. Now in this facing operation, you can select the features that you'd like to face. So you can either use select curves, flat areas, or predefined regions. We're going to use select curve edge regions, and I could right-click on this face edge and then use the selection tools that are available in SolidWorks using like select loop or select tangency or select chain. In this particular case, I'm going to pick the chain of edges in here on the top face of the part by using select loop. So I'm going to go ahead and accept my selections, and you'll notice that those 4 face edges are automatically being selected in here. The next step is to specify a tool for it, so let's go ahead and pick a face mill tool. You can also edit, create new tools, add new tools in here by going over to your Create Edit Tool Selection dialog. You can specify the properties for each tool, assign your tool numbers, select the material for the tool, and then under the Feeds and Speeds tab, you can also establish your feeds and speeds. You can either enter in the feeds and speeds or use the built-in feeds and speeds calculator by using the load from file option, and depending on the stock and the tool material and based on the properties of your stock material, which is the surface feed and the feed per tooth, VisualCAM can help you estimate feeds and speeds. So once you have the tool selected, we would then go to the feeds and speeds tab to load the feeds and speeds from the tool. In the next step, you would want to establish your clearance. When this tab is active, the clearance plane is displayed on top of the part, and by default it's set to automatic, which will automatically clear the maximum height of the part or the stock based on the geometry. The next step is you would go over to the roughing tab where you can specify the parameters for your facing operation. You can set your tolerance, your stock allowance, your cut pattern, your cutting direction, your step over distance, and in the cut levels tab you can specify your total depth. So I can specify the top of cut to begin at 0, and then the total depth, I'm going to set it as a 1/4 of an inch. Now if you'd like this to be cut in just one pass, you can specify the total depth to be the same as your rough depth, or if you'd like to face it in 2 levels, you can specify your rough depth cut in here. The entry and exit tab allows you to specify your entry and exit motions, and then selecting generate creates your toolpath. And there's your facing operation. The toolpath is automatically displayed on top of the part. You can toggle the display of your toolpath, and you can also view the toolpath in levels. You can see that there's 2 cut levels, an 1/8 inch, and then down to a 1/4 inch. Now let's go run a verification of the toolpath. So let's switch over to the Simulate tab. You can select the operation, and then click on Play, and that gives you the verification of the cut material simulation. You can also slow down the simulation, and then select Play again to go back and run the verification. Now, if you'd like to make any changes or edits to any of these parameters in here, you can double-click on this operation and make changes to all of the properties, the parameters of the facing operation. Now, once the operation has been programmed, we could go ahead and program the next set of operations. So we would like to go ahead and program these pockets in here. We'll go over to 2-axis and use pocketing. The workflow is very similar. You specify the features you'd like to pocket. So here I'm going to right-click and use Select Loop to select the features to pocket right there. And then accept the selections, specify a tool for it. So we'll go with a 1/2 inch cutter. We'll set the feeds and speeds and clearance, specify your cutting parameters, choose your cut pattern, your step over parameters. In the cut levels, you can actually pick the depth from the 3D model by just snapping to the top face, and then I'm going to select the floor of the pocket. There is our pocket right there. It's a 1/4 inch deep. I can specify the entry and exit before I hit generate to compute the toolpath. Now there is our pocket toolpath for the first step on the part. So let's go ahead and run a verification, and there it is. If you'd like to speed up your simulation, you can always select the pause and then click Simulate to end to run through the simulation. Now since we have another pocket that needs to be programmed, here's what I'm going to do is select this operation that we already programmed, right-click on it to make a copy of it, and right-click on it again, and we'll select Paste. Now the same pocket operation is copied. I'm going to modify it by double-clicking on it to edit the pocket operation. Now I'm going to use Remove All to remove the existing selections, and then we'll go back and reselect the inside boundary of this pocket in here by using Select Loop. And I'm also going to go over here and pick the top edge around the island by using the Select Loop command again. So we have 2 edges selected in here. Once you have those 2 selected, in the next step we'll utilize the same tool. We'll go with the same parameters for the feeds and speeds and clearance. And then in the cut levels, I'm going to pick the depth of the part by picking the top face and then the floor of the pocket. You'll now notice that the total cut depth has been updated automatically. And now, since we also have an island on top of this part in here, I'm going to use this feature called Clear Island Top. So it'll automatically add an additional pass to clean up the top face of the island. And you can also notice that the top face of the island is not at the same height as the top face of the pocket. So the system is automatically smart enough to figure out the height of the island and add an additional pass to clean that out. Let's select Generate, and there's your pocket toolpath for the inside feature. And if you step through the levels, you will notice that it automatically added an additional pass to clean up the top face of the island. And let's go ahead and run a verification in here. So select Play, and that shows your cut material simulation for the second pocket operation we just programmed. And you could always select the pause and simulate to end to run through the simulation. Now finally, I would like to go ahead and program a profile operation in here. We'll select two axes and use profiling so that we go back and clean up the stock we left on the sides of the part. We'll do a profiling operation. And then for the geometry, I'm going to use select flat areas and just pick the floor of this part right there and accept it. So you can either use dry regions by selecting face edges, or you could use flat areas, or you could use predefined regions. The next step is to specify a tool, so we'll still use the same 1/2 inch end mill. We'll set our feeds and speeds and clearance. Under the cutting parameters, I'm going to choose my cut direction to be climb, and for the side to cut, I'm going to use determine using 3D model. So the system will automatically determine which side to place the cutter, since you need the cuts to go on the inside on one of these outermost boundary and outside of the innermost boundary. So selecting determine using 3D model will automatically determine which side to place the cutter on the profile operation. Next, you could specify your cut levels. If you just want to do it in one level, you could specify the cut depth to 0, and then we can say the geometry what you selected is at the floor of the pocket, so we choose at bottom. We would then specify your entry and exit, and then select generate. And there's your profile operation right there, which cleans it out. So let's go ahead and run a verification in here, and there it is. So once you have all of your toolpaths operation programmed, you could save your work, and all of the machining operations are saved with the same part document in SolidWorks. You could take a look at your estimated machining time. Right mouse button click and selecting information will give you the total time for machining this part. You could also generate a shop documentation. Right click and then selecting shop documentation will generate a setup information sheet, which includes information about your tool, your machining operations, the stock geometry. That would be very handy for the programmer in the shop floor to get things organized in here to basically mill this part out. So you can see that there's your shop documentation right there. Lists all the tool list information, has information about your stock dimensions, and gives you a preview of each and every operation that you just programmed. And finally, we would like to go ahead and post-process the toolpaths. So we'll select the operation in here, right-click, and then select Post. And this automatically outputs your G-code. And by default, it posts it in the same folder where you had the part loaded and uses the same name as the part name. And there's your posted output file. You can then transfer this out to your machine controller. So this basically gives you a quick overview of how you can program toolpaths in 2.5 axis using VisualCAM for SolidWorks. Next, we're going to go ahead and take a look at some of the other nice methods that are offered in 2-axis milling before we turn our attention into 3-axis milling in VisualCAM for SolidWorks. So we're going to take a look at a method called high-speed pocketing, which is a very nice way of programming pockets. In this particular high-speed pocketing toolpath method, the toolpath is generated with a spiral pass, and then it creates constant tangential cutter path, which basically creates a constant cutter engagement, which helps in prolonging tool lives as well. So let's go over to 2-axis machining, and we'll select the high-speed pocketing. Now these methods are offered in all configurations of VisualCAM for SolidWorks. VisualCAM for SolidWorks mill module has 4 different levels or configurations. We have standard, expert, professional, and premium. So the high-speed pocketing and the facing and the pocketing operations we looked at in the previous examples are offered in all configurations. Now with the high-speed pocketing operation, I'm going to go ahead and select the features. I'm going to use select curve edge regions, and I can just right-click and use select tangency in here to automatically select all of these features. So right-click and do a select tangency. We'll automatically pick all the chain of the edges in here. And then we'll go to the tool. We'll use a tool for programming this part. So we're going to use a 1/4 inch end mill, set the feeds and speeds and clearance. In the high-speed cutting parameters, you can specify a cut direction. And if you'd like to add a cleanup pass, you can select it to add a cleanup pass and specify your step over in here. Next, we'll go over to the cut levels, and we'll specify the location of geometry to be at the bottom, which is the floor of the pocket. And then let's go determine the depth by just selecting the top edge and the floor of the pocket. The total depth is a 1/4 inch. And if you'd like to break this up into 2 levels, you can specify your depth per cut, and then selecting generate creates your toolpath. So there's your high-speed pocketing toolpath. Take a look at the toolpath. It starts with a spiral pass and creates constant tangential arcs. So you can run these at higher feed rates, which basically creates constant cutter engagement and prolongs your tool life. And there is your high-speed pocketing simulation. Now, one of the nice features of working within an integrated CAD/CAM system is the ability to make design changes and not have to go back and redo all the toolpaths. So in SolidWorks, since you're working within SolidWorks to create all your CAD design, you could make design changes as required on your parts. I'm going to go ahead and modify this pocket in here, and I'm going to use the direct editing feature so I can modify the part. So I'm going to basically change the pocket. In here you can see that I've made the pocket larger. So as I make a design change, you will notice that it automatically marks the operation you just programmed as dirty. So which means since we use the drive edge, the face edge of the part of the drive region, it has been automatically updated. So I'm going to right click and then do a regenerate, and you'll notice that the toolpath is now automatically updated to reflect the changes what you just did in the part. So working with an integrated CAM system, CAD/CAM system, allows you to make your design changes, and you could, update your toolpaths by just one click of a button in most cases. And when I go back and rerun the simulation, your toolpaths are updated for the changes what you just did. Now, if you go ahead and undo those changes in your CAD, you could just go back and regenerate your toolpath again, and it'll automatically update the toolpaths for the changes you just made. Now let's go ahead and hit save our work, and there's your high-speed pocketing toolpath. Now folks, if you do have any questions during this webinar, please do feel free to post your questions in the questions panel, and we'll try to get those questions answered as they come along. Now let's take a look at our 3-axis toolpath methods that are offered in VisualCAM 2016 for SolidWorks. VisualCAM 2016's mill module offers a wide range of 3-axis toolpath methods, starting with roughing, finishing, and several different types of finishing methods. Now, the methods that you're looking at here are all available in Pro and Premium configurations. With our standard and expert configurations, roughing, parallel finishing, horizontal finishing, radial and spiral machining are included in addition to 2.5-axis methods. Now, a part that's typically has sculpted surfaces, complex 3D surfaces, fillets, radiuses on the part, drafts on the part would be ideal for programming in as a 3-axis toolpath. Now the workflow is very similar to how we programmed our 2-axis toolpaths. In the first step, we are going to define the machine tool and pick the number of axes. We're going to set it to 3. The next step, we're going to go ahead and select the post processor, which we already have it set to Haas, and then I'm going to use the stock material here, and we can select the stock type as a box stock, and the system will automatically determine the stock extent space of the part that you imported in here. So I'm going to modify the stock height or stock thickness to 3 3/4, and then pick OK to accept it. So you will now notice that the stock has been defined, and let's go ahead and align the stock. We're going to have it aligned to the bottom center right there. In the next step, we are going to establish the origin. So I could leave the origin where it is, which is at the lower left corner and the bottom of the stock, or if you'd like to have the 0 set to the top face of the stock, you could move it to the top face of the stock. Now for this particular part, I'm going to leave the work 0 to be at the same location where the origin is located, and then pick generate. In the next step, let's go ahead and look at our 3-axis toolpaths. Now, typically, when you're starting out with a rectangular blank or a large piece of stock, you'd want to rough it down so that you bring it as close as possible to the finished shape of the part. So we're going to start that by using a method called horizontal roughing. This basically is also known as roughing in levels or Z-level roughing. So in this particular method, the system automatically takes into account the part and the stock geometry that you've defined to determine your toolpaths. Now, under the Containment Regions tab in 3-axis operations, you can select containment regions if you'd like to contain or limit toolpaths to specific areas. Now, in this particular case, since we are looking to rough out the entire stock blank to bring it as close as possible to the finished shape of the stock, I'm going to skip the process of selecting the containment region, so the system will automatically take into account the part and the stock geometry. In the next tab, we're going to make our selection for the tool. So I'm going to use a 1/2 inch end mill. We'll specify our feet and speeds in here, and then we'll go to the clearance to set the clearance to automatic. In the next tab, we're going to define the cutting parameters where you can specify your tolerances, your stock allowance. So I'm going to leave at least at 25,000 stocks so I can use my finishing operation to finish them up. And I can choose my cut pattern in here. So I'm going to use offset cut pattern, and I've already selected to use the facing cut pattern based on core region. So based on core and cavity, the system can automatically determine to either do a facing or a pocket operation. We're going to set the cut direction to mixed, and we'll do a step over of 40% of the tool diameter. And then we'll go over to the cut levels tab where we can specify the step down control. And if you'd like to contain the toolpaths and not have it cut below a certain Z, you can use these containments in here. Let's go ahead and select generate, and you'll now notice that the roughing toolpath is computed based on the part and the stock geometry. And there's your roughing toolpath. You can also view the toolpath as you step through each of the levels. You can see that it does a Z-level roughing based on the step-down parameters that were set. Now let's go ahead and run a verification. So let's switch over to the Simulate tab, and then you can select the play button, and there's your roughing toolpath. And if you also like to speed up the simulation, you can use the controls under the Simulate tab to slow it down or speed it up. And you can always select the pause button in here and then use Simulate to end to automatically have it run through the simulation. And there's your in-process stock after you completed the roughing operation, programmed roughing operation. Next, we would like to go ahead and program the finishing operation. So ideally, I could use a combination of different operations. So let's start out with a parallel finishing toolpath. So I'm going to use 3-axis machining and choose parallel finishing. And in order to restrict or contain toolpaths, you can specify either a selection of chain edges, curve edges, or you can use a flat area. I'm going to use a select flat area option in here and just go pick the floor of the part, and I'm going to accept it. You'll now notice that the system automatically puts a boundary around the entire part to contain it. We'll go with the radius tool. So in this particular case, I'm going to use a ball mill. Let's say I want to use a 1/2 inch ball. Specify the feet and speeds. Set the clearance definition in here. And in the cutting parameters, I can set the tolerances. And you'll notice that the stock by default is set to 0, so we want to finish it right to the finished surface of the part. You can control your cut direction, specify your cut start side. We'll do an angle of cut. I'm going to use 45. And for the step over, I'm going to set this to 20, and then we'll pick generate. So in this process, a parallel finishing operation is now generated, and you can view the toolpath once it's computed right there. So there's your parallel finishing toolpath following the surface of the part geometry. There it is. Now let's go over to the Simulate tab and run a verification of the cut. So you can select the play button, and there's your simulation of the parallel finishing toolpath. There it is. Now you can use the parallel finishing operation either as a finishing or a pre-finishing operation. You can specify to leave some stock and then go back and rerun the parallel finishing operation, or use one of the other finishing methods to create a final finishing operation. Again, if you'd like to skip through the simulation, you could always select the pause button in here and then pick Simulate to end, which will automatically run through the simulation. And you'll notice that the progress bar down below here is automatically updated once the simulation is complete. So there's your parallel finishing operation in here. Now you can also create additional operations to go back and limit toolpaths to specific areas. For this, what I'm going to do is go ahead and load in a part which currently has a few other operations programmed, and we'll go ahead and take a look at those. Now, folks, while I'm trying to bring in the other part, if you do have any questions, please feel free to post those questions in your questions panel, and we'll try to do our best to get them answered for you. Now here is the same part what I have. I've added a few other operations. I've created a radial machining operation by basically selecting an area to contain the toolpaths. So I've selected a chain of edges as our drive geometry to restrict the toolpath. Now with our advanced 3-axis module, which is offered in the Pro and Premium configurations, you have more options for programming toolpaths, like the one that I'm showing here is the 3D offset pocketing, or also known as constant scallop machining or constant 3D step over. We also have methods where you can program between two curve machining, so you can pick two curves. It could be either closed or open, and the toolpath will basically morph between those two curves following the 3D geometry. We have pencil tracing and remachining methods, which can be very effective in cleaning up areas, which automatically the system determines the bitangencies based on the part geometry. So these advanced 3-axis methods are offered in the Pro and Premium configurations. Now, if you visit our website, go over to the feature list, you'll be able to take a look at all of the different methods offered in each configuration. We did have one question from one of our attendees. Is there any advantage of using a 45-degree cut on the parallel finishing? I just chose a 45-degree as one of the options in here. You can basically determine the angle or the direction of cut based on the type of part geometry you're working with. So you could either go with angle of cut 0 or 90. In this particular case, I chose 45. So basically, it goes at a 45 degrees from the x-axis. You could change the angle to maybe 135, so you can go back and clean it up in a cross direction, so which basically cleans up any scallops that might be left from a different cut, from the original initial cut pattern. So the angle of cut is determined based on the type of part, based on the type of features you're trying to cut. So so that the toolpath is basically generated in these parallel planes following the angle of cut. So when you have a lot of these steep sections on the part, you may want to go at an angle that's across from the steep section and not parallel to the steep section. So that would result in a better finish on a parallel finishing toolpath. Now, folks, I did notice that one of our viewers have asked if tabs are available. They would like to take a look at it. Yes, we do have tabs in 2-axis operations, and I'm going to go over those as I cover some of the new features of 2-axis methods. So please be patient, and we will definitely get to the topic about how to create bridges and tabs. So this basically gives you kind of an overview of the 3-axis methods that are offered in VisualCAM's mill module. If you do have any questions about it, please feel free to drop your questions in the chat window, and we'll try to get them answered out to you. Next, I would like to go ahead and showcase some of our 4-axis methods that are offered in our VisualCAM's Expert and Pro configurations. Now, 4-axis methods are ideal for parts that require machining from, at least more than 2 sides. Now, if you have a machine that has a rotary axis or a rotary table, which can turn the part along your rotational axis, which could be either along the x-axis or along the y-axis, you could define your machine tool definition to be as a 4-axis machine, and you can specify your rotational axis. Now, this could be either on the x-axis. You'll notice that when the rotation axis is selected, a green arrow appears indicating the direction of your rotational axis. This could be either plus or minus x, or it could be oriented along plus or minus y. So in the 4-axis methods, your tool remains normal to your rotational axis. So once you define the machine, we would select the configuration as table, which is the most commonly used configuration for 4-axis. So once you establish your machine, you'll notice that the machine type is automatically updated. You would then go ahead and select your post processor and then define your stock. Now for this particular part, we're going to be starting out with a piece of rectangular block. You'll notice that the stock is defined as a box stock in here. And I've also added some supports to the end of this part. You could either be working with parts that are created in SolidWorks, or you could be working with parts that could be imported into SolidWorks from, model, which is the part could have been modeled in a different CAD system. So in this particular case, we've also added some supports to it. Now, typically, to rough this out, you could use the index technique where you can lock the rotary table into a specific orientation and program a 4-axis indexed roughing operation. So you can create indexed operations by creating rotate table setups where you can rotate the table and lock it into a specific angle or orientation and then program a toolpath. So what we have done here is we've created a 3-axis roughing toolpath, as you can take a look at right here. And in the roughing operation, we've set a containment for the bottom cut level not to cut below the center line of the part. So since the part is going to be machined from 2 sides, we want to limit the roughing operation in the Z only to go halfway down. So I'm going to hit the play button to run the simulation. So once the simulation is completed on the roughing operation, you will see that it's only roughing halfway down. Now once you have the roughing completed, you would want to go ahead and rotate your table using the rotate table setup operation. And right in here we have the table rotation angle set to 180 degrees. So you will notice that the rotary table is turned on the machine tool, so which basically turns the part over by 180 degrees. And now you can basically program the same roughing operation from the bottom half of the part. So the part gets turned over on your rotational axis, and you can rough it out from 2 or more sides. In this particular case, the rotation axis is set to 180 degrees, so we can rough it out just from 2 sides. Now once the rotation is locked in, the roughing operation is processed, you can go back and change your rotation angle in here. So in this particular case, we've turned it back to 0 degrees using another rotate table setup operation, and then we can program a combination of index and continuous operations. So parts like these are ideal for 4-axis continuous finishing operations, and you can access all of the different 4-axis methods by going to the 4-axis menu here. You have 4-axis parallel finishing, finishing in levels, projection pocketing, 4-axis engraving, and for parts that have a constant radius, you can use 4-axis facing, pocketing, and profiling. These are similar to like the wrap methods, similar to your facing, pocketing, and profiling in 2-axis. So we have the 4-axis parallel finishing operation in here, where basically we have set the cut direction to be along the axis of cuts. And if you'd like to specify any axial containments, you can specify an axial containment to limit the tool paths. You can notice that in this particular case, you've set it a low and a high value to limit the tool path so that the supports are still retained after the 4-axis parallel finishing operation is processed. And the angle or containment can be set to 0 to 360, which is the default, or you can limit it to a specific range of angle in here. So we now have the 4-axis parallel finishing operation program, and selecting the play button shows the cut material verification. And there's your simulation for the 4-axis parallel finishing operation. I'm going to hit the pause button to pause the simulation so you can see the finishing operation in progress. Next, I would like to turn our attention over to our 5-axis methods to give you a quick overview of some of the very nice 5-axis methods we have in our Pro and Premium configurations. So first, I'm going to go over the index 5-axis methods, which is also known as 3+2 machining. So you can actually program parts from different orientations without having to create multiple copies of the part. In the case of index 5-axis setup, or also known as 3+2 machining, you could define your machine tool to be a 5-axis, and if you have a 5-axis machine, you can specify the type of configurations. It could be a head configuration, a table head configuration, or a table, which could be like a trunnion style machine. You specify the number of axes, and then you pick the primary and the secondary axis for your 5-axis setup. In the next process to program index, this is very similar to how we did the rotate table setups. Here, rather than using the rotate table setups, we're going to use what is called the CSYS setups to create the indexed operations. So you would basically orient your coordinate system to the top face in here, in this particular case, and then we would program all the operations for the top face. We have roughing and finishing operations for the top face. In the next step, we can add a new setup in here by going over to the coordinate system setup, and we can reorient the coordinate system, and in this particular case, we have it oriented to the front face. So once you reorient your coordinate system, you could program tool paths from that particular orientation. So this is called indexed, or also known as positional 5-axis, or also commonly known as 3+2 machining. So you're basically locking the tool axis to a given orientation and programming 2 and 3-axis tool paths. Now once you have all of these tool paths programmed, you can go ahead and run a verification. So right-click and then select Simulate All. We'll run a verification from all the different orientations. Now, if you have a 5-axis machine tool, you can post-process the entire operations to one output file. Now, if you're working with a 3-axis machine tool, you can still create additional setups, but you would have to refixture or reorient the part and then post each setup out separately. So the Pro configuration offers the feature to be able to create multiple coordinate system setups, so you can basically reorient your coordinate system to any given orientation to program the part. Now, we're going to talk about the simultaneous 5-axis methods, which are offered in our premium configuration of VisualCAM for SolidWorks. Now, this is a solid surface-based machining module where you can generate true 5-axis toolpaths or simultaneous 5-axis. So typically, you would be starting out with a roughing operation. So in this particular case, we have a 3-axis roughing operation program. And you can access all of these simultaneous 5-axis methods by going over to the 5-axis methods menu. And we have different types of 5-axis methods, starting with curve projection, flow curve, between curve, drive curve, surface normal, swarf machining. So in this particular case, I'm demonstrating the swarf machining toolpath. And you'll notice that the simulation here shows the 5-axis motions on this particular part being programmed. To learn more about our different configurations, select the Feature List tab on the VisualCAM for SolidWorks products page, and you can get a full list of the toolpath methods that are offered in each configuration. Next, I want to demonstrate our 2-axis, the turn module that is offered in our VisualCAM's turn module. We'll go through an example where we're going to take a look at the different turn methods that are being offered. So let me go ahead and bring it apart, and without any further delay, I'm going to go ahead and create some toolpaths in here. So folks, if you do have any questions during this process, please feel free to go ahead and post your questions, and we'll try to get them answered as quickly as we can. Now, our turning module offers 2-axis programming methods, so you can effectively program turn roughing and finishing operations. Now here I have a part which basically requires turn programming on it. So in order to switch from the milling module over to the turn module, you can either select the turn browser or click on the mill button on the program tab, and this will automatically switch the interface over to the turn module. So here I have a part which is ideal for turn programming. Now the typical steps involved here is the workflow is very similar to how we notice in the mill module. You'd go ahead and define your orientation for machining. So in our turn system, we automatically orient your world x-axis to be your turn z-axis, and the world y-axis is automatically oriented to the turn x coordinate system. But if you need to change the orientation, you can use these controls in here to reorient your coordinate system for machining. Now once you have established your coordinate system, the next step is to select the post processor for your turn machine tool. You can select it from the list of post processors in here, and also additional posts can be added. In the next step, you would want to define your part, so you can either use select surfaces, or you can select sketches or curves to define the parts. In this particular case, we've selected the entire part to define the turn part, and you can see that the system automatically determines the cross section of the profile of the part. Now, if you'd like to view the part in a sectional view, you can use a sectional view in SolidWorks to take a cross-sectional view of the part right there. Now, there's the part that's defined. In the next step, you would want to build your stock materials. We'll go over to the stock and cylinder stock, and there's your cylinder stock. So we're going to use a stock radius of 1.5 inches, and the overall length is set to 3.22. Now, once you establish the part and the stock, you can view the stock in the Simulate tab. You can also look at the stock as a full 3/4 or a quarter view. So if you have features that require ID features that needs to be machined, a 3/4 view might be ideal for viewing it. And you can go over to your operation to create the work zero. So typically you would want to set to 0 to the rightmost face in turning, which is the rightmost face of the blank. You can select stock box rightmost. And if you'd like to output this as your work offset G54 or 55, your work coordinate offset, you can select that and then click generate. And there's your work zero being set to the rightmost face. Now you have turning operations starting with roughing, finishing, groove finishing, follow curve, threading, and parting up operations. So you can basically program each of these operations in here. So I currently have some operations programs. I'm just going to go through the process of generating those toolpaths in here. And you can also contain the toolpaths by specifying boundaries or regions to restrict the toolpaths. And these options can be set in the global parameters. In this particular case, I'm trying to avoid this groove section in here, so I have an avoid section selected. So to avoid the groove from being programmed in the roughing and turn roughing and finishing operations, and I've had a separate groove operations to basically to program those grooves. And you can go to the simulate tab and then hit the play button to run the verification in the turn module. So you can program outer diameter, inner diameter, and face operations in turning. Now, you can also generate a shop documentation, very similar to how we did in our mill module. You can generate a shop documentation in your turn module as well. And once the document is created, it'll automatically appear in your HTML viewer or your internet browser, whatever is set as default in your computer. And there it is. There's your setup information sheet, has information about the tools, the inserts we're currently using for programming this part, and lists all the different operations that are currently being programmed. Folks, as we are going through a lot of different features in here, so we may be running a little over time than our webinar, so please do bear with us, so we'll be able to get through all the different features and go over them. Now, finally, you would want to post-process it to your machine. Now, in turn programming, you can either program it in radius or diameter mode. So if you go over to the machining preferences, you have an option to do it in a diameter mode programming, and then when you post it out, your X coordinate values will automatically be in diameter mode, and there's your posted output file right there. And this can be transferred out to your machine. Now again, saving the part in SolidWorks automatically saves all of your machining operations to the same part file. Now, the next thing I'm going to go over is our hole feature detection in two-axis methods. And I'm going to go over that, and then we'll take a look at the new features in VisualCAM 2016 for SolidWorks. Now, the hole feature method is a very nice way of identifying holes and automatically programming holes of similar types. Now, I'm going to switch back into our mill module. Now, the hole feature detection is available in all configurations of our mill module. Now, the part I currently have loaded has several hole features, the hole patterns in here. So the best and easiest way to program this would be by going over to the Features tab. First step is to identify the features. So I'm going to use this command called Create Hole Features, and then just pick the top face of the part where all the holes are, and I'm going to accept it. Now you'll notice that the system automatically identified two types of hole features. And as you expand this tree, you will see that there are 6 instances of each in this hole feature. So the hole feature 1 has the counter bore and the through hole, and then the hole feature 2 has just the drill hole. Now, to be able to program toolpaths for these hole features, once you have identified the hole features, you can click on Create Hole Feature Machining Operation, and this automatically displays the cross-section of the hole that you're trying to program and gives you the available operation types that you can use for programming it. Now, in the first step, what I would like to do is like a spot drill or a center drill operation, so I'm going to just drag and drop this operation over here from the available operations to the desired operation. And in here you can see that it automatically displays the diameter of the hole, the cross-section of the hole, and also the depth. So I'm going to change the parameters in here, and you can specify how deep you want it to do the spot drill operation. So I'm going to leave it at maybe 75 thousandths for the center drill operation. In the next step, I want to drill all the way through. I'm going to use a deep drill operation. Just drag and drop the operation in here, and then specify. You can see that the depths are automatically being set based on the cross-section of the hole. Finally, I would like to go ahead and pocket or profile this counter bore. I'm going to use an operation called two-axis hole profiling. So I'm going to drag and drop the hole profiling operation into it and set the total depth right in here. So once you establish these workflow for this particular hole feature, I'm going to select the Create Hole Feature Mop Set, and you'll notice that this operation set now appears under your setup. So you basically have a center drill, a deep drill, and a hole profiling operation. Now, if you'd like to make any changes or would like to change some of the tools for it, you can use these options in here to replace the tools if needed. So what I'm going to right-click and do is generate the toolpaths. You'll now notice that the hole feature operations have been successfully generated for this particular features that have been identified in this particular part. Now, how can we automate some of these processes so that when you have parts that have identical hole features, how can we reuse the same operations rather than having to go back and recreate it? So what we're going to do here is now take this hole feature operation set and save it out to a knowledge base. I'm going to click on Save to Knowledge Base, and then I'm going to save this under the Program Data folder for VisualCAM, and go over to the Whole Feature Machining Knowledge Bases folder, and I'm going to save it by specifying a name for it. So I'm going to just leave it the name as Whole Feature 1, and I'm going to select Save. In the next step, what I'm going to do is go back and open up another part which has similar hole cross sections. So I'm going to go look for another part in here which has hole features that have similar cross sections right there. You can see that this particular part, even though it's not a part that looks similar or identical to what we have, but the whole feature cross-section seems to be appear to be similar. So let's go ahead and first identify the whole features. So we're going to use the Features tab to click on Create Whole Features to identify these whole features and accept those. And you'll now notice that it automatically identified a whole feature and has 6 instances of it. Now in the Whole Features tab, you have an option called Select Matching Knowledge Base and Create Whole Feature Machining Operations. When you click on this button, the system will automatically go look for whole features that exactly matches the cross-section in the folder where you had it saved, and you'll notice that it automatically generated an operation for each of those whole features. So this basically saves you programming time when you have the same whole feature cross-section on your different types of parts that you're going to program. So you can basically automate your process of programming holes by using the whole feature detection and loading the whole features from a knowledge base. So this is a very powerful feature that's available in all configurations of our VisualCAM for SolidWorks mill module. Now, I did have one of our customers or users, attendees, ask about how do we create tabs in profiling operation. So when you go over to 2-axis and profiling, you can select your geometries that you'd like to profile. So I'm going to use Select Loop to basically go ahead and select the chain over here and accept it, and then specify a tool for it. In the cutting parameters, I'm going to choose the side to profile as outside, and in the cut levels, we're going to specify the top of cut to be the top face of the part, and then the total depth, we're going to go from the top face down to the bottom edge, and we'll specify to go in a 1/4 inch step increment in Z. And then in the advanced cut parameters, you can specify to use bridges and tabs. You now have the option to either do a triangular bridge or you can do a rectangular bridge, and you can specify your bridge height. So I'm going to put in a bridge height of 0.2 and give it a bridge length as 1 inch, and you can specify the number of bridges. So if you want to have 4 bridges, you can select that and hit generate, and this will automatically create 4 bridges, and you can see those 4 bridges are created automatically around the entire geometry. Now, if you'd like to be able to specify or control the location of bridges, what you could do is you can create a predefined region. So here I'm going to use a surface edge boundary in here to basically define a predefined region, and you can go ahead and specify the location of your bridge points, where you'd like the bridge points to be placed. You can click on Select Bridge Points in here by using Manual Bridge Point Selection, and you can pick the location of bridge points where you'd like to have the bridge points placed by just graphically selecting points along the curve. And once you have those points defined, you can accept the selections. And then in your profiling operation, you just go ahead and select the predefined region as the drive geometry rather than selecting a curve. And when you select Generate in this particular step, you'll notice that the bridges are created exactly where you selected those bridge points. So there are your 4 bridges being created, and I hope I was able to answer your question about how to create bridges and tabs in profiling and being able to select bridge points at the desired locations. Next, I would like to go over some of the very nice new features and enhancements that have been added to our 2016 release of VisualCAM for SolidWorks. First feature I'm going to talk about is a new method called 2-axis and roughing. Now, this is offered in all the configurations of our mill module. So I have a part that currently has several features that needs to be machined, and I'm starting out with a stock blank that's much larger than the part. Now in our previous versions, we had to create an additional sketch geometry to define the extents of the stock and in order to program a facing operation. So what I'm going to show you here is how the system can automatically detect the extents of the stock, and what you'd be selecting is just a part boundary to program the toolpath. So I'm going to go over to 2-axis and use roughing, and in this particular case use select curve edge regions to define the extents of the part. So I'm going to right click on this edge and use select loop to select the entire loop right there as the boundary and specify a tool for it, and then selecting generate, you'll notice that the system automatically determines the part extents, and it knows where the stock geometry is, and it figures out a roughing toolpath. So this is a very nice way of roughing, creating roughing 2-axis using 2-axis roughing operations rather than having to create additional geometries for creating like a facing operation. So you can use this also to be able to program the inside features. You can go back in here and say you want to also program this pocket, so you can select the loop right around it, and if you want to specify any containments in the Z, you can use the bottom containment and say you don't want to cut below this face, and then pick generate, and there would be your pocketing operation. So you can basically go back in here, select the features that you want to cut, right click and do a select loop and specify the features to be cut, and then hit generate to program your toolpaths. So you can use a 2-axis roughing technique to program it effectively. Now this feature is offered in all configurations of the mill module. Now in the pocketing operation, we made several enhancements in pocketing operation. So if you go over to 2-axis and pocketing, you now have the option to specify corner cleanup loops. You can do inside and outside corner cleanup loops in pocketing. So if you want to do a corner cleanup with the inside, I'm going to go select this feature and right click the select loop to select the feature right there, and then selecting generate, you'll notice that the system creates a corner cleanup loop on the inside right there. So these are high-speed cleanup loops. Rather than just doing a linear or straight connections, you have a nice corner cleanup loop on it. If you want to switch the loop to be on the outside, you can switch the loop to outside and then generate it, and this creates an outside corner cleanup loop. Now this is offered in 2-axis pocketing as well as in 3-axis roughing operations. So these are some of the new features that are added in roughing and pocketing operation. Next, I would like to go over one of the new features that's offered in our profiling operation, which is basically automatically selecting the midpoint of the longest segment for programming profiles. So I'm pretty sure you remember this part we looked at earlier, and in this particular part, what I'm going to demonstrate here is in our profile operation, you have an option to automatically have the system use the midpoint of the longest side to determine the location for entry and exit. So when this is selected and when we generate the toolpath, you'll notice that it automatically, the system uses the midpoint of the longest side of the geometry that you selected for the location of entry and exit. So you don't have to go and manually pick the entry and exit locations if you just want the system to automatically determine the midpoint. Also, there have been enhancements added to 2-axis profiling operation where you can use mixed cuts as it alternates between levels. So you can go between climb and conventional between as you step down between levels. That's one of the newer enhancements in profiling. And also in your entry and exit operation, you can also specify a angle, a ramp height. So in addition to just doing a 2D entry and exit, so the along path will basically ramp along the path of the curve. However, if you use lines and arcs and you specify a height to it, so for example, if I want to use the entry type to be linear and I will specify a height to it, you'll notice that for both the entry and exit motions, it'll do a ramp along a 3D away from the part. So you can see that in the entry and exit parameters, in addition to just doing a 2D linear, it's also doing the ramp along it. So you can use this option in here for your entry and exit in 2-axis profile operations. Now this basically showcases some of the very nice features in the new enhancements in 2-axis operations. So the next thing I'm going to go over is the enhancements that are made to the 3-axis operations in here, especially the parallel finishing and the horizontal finishing. So what I'm going to do here is go ahead and bring in a part which has a horizontal finishing operation that's already was programmed in our older versions of our mill module. So you can take a look at that. I have an operation called horizontal finishing 2015. Now you can see that with the optimized machining turned on, there were so many read tracks with the optimized machining toolpath in the older versions. Now with the new version, I'm going to make a copy of this operation, and I'm going to go back and rename it and just quickly regenerate the toolpath in here. So when I regenerate the toolpath, you will see that it'll minimize the retracts to as minimum as possible. So it basically reduces your machining time and makes it a lot more efficient. So this is one of the newer enhancements in the 3-axis methods. You can see that it reduces the number of retracts from what used to be when you have optimized machining turned on. Also, with the 3-axis parallel finishing operation, we now added options to ignore holes on planar faces. You also have an option to machine just tops only or tops and sides. So let's go ahead and program a parallel finishing operation for this particular part in here. And I have set the angle of cut to 45, and I've choose tops only. You can see that only the top faces features of the part are being machined. Now if you go back and edit the parameters and change the cutting area control to top and sides, this will also be able to program both tops and sides with the parallel finishing operation. This is also one of the newer features that are available in all configurations of our mill module. Folks, one of the cool features I want to show is the automation of knowledge bases in our VisualCAM mill for SolidWorks product, and I'm going to show you how this works. And in order to demonstrate this, I'm going to go ahead and load this part in here, which basically has a pattern of holes or several hole features on it. So I'm going to go ahead and load in a knowledge base of operations that were programmed already. So I'm going to click on load a knowledge base, go to the hole features, and load this knowledge base called holes, and then click open. You'll notice that I'm being prompted with this dialog saying there were no rules set for it. So I'm going to select no, so I'm not going to set any rules when I load the files from the knowledge base. And you'll notice that in the knowledge bases tab, we now have 3 different operations in here. So we have a standard drill, we have a deep drill, and a hole profiling operation that was created in a knowledge base. Now when I expand this operation, you have an option to specify rules for the operation. So the next time I load a knowledge base on another part, it can automatically select machining geometries based on the rules that we put in. So in order to specify rules, I can double click on this and specify rules for it. Now for the standard drill operation, I would like to basically drill all the holes. So I'm going to select them as circles in here and then give it a range. So first thing is I want to drill these through holes in here and specify a range for it. So I know the holes are about 1/2 inch in diameter, so I'm going to give it a range of 0.45 to 0.6, or maybe I can put in a range of 0.4 to 0.6 right there and set the rule for the standard drill. Similarly, I'm also going to set the rules for the deep drill operation. So these holes in here are 3/8 of an inch in diameter right here. So I'm going to specify a rule for those holes as well by giving it a range for the holes. And finally, I would like to profile these counterbores, and I'm going to specify a rule for that as well by specifying a diameter range. I'm going to use 0.7 to 0.8 because those holes are about 3/4 inch in diameter. Now once I have these set, what I'm going to do here is in the feature tree, I have some sketches created on the model. I'm going to show or make those sketches visible in here. Now you'll notice that the operations have been assigned with rules. As I drag the knowledge base over to the machining browser from the operations browser, you'll notice that it automatically has selected those geometries. All I got to do is right click and regenerate, and you'll notice that the toolpaths have been computed and the geometries have been automatically identified and added to each of those operations. So when you edit the operation, you'll notice that it automatically selected all the holes of 1/2 inch in size to program the drill operation. Similarly, it has done it for the deep drill and the hole profiling operation. Now what I'm going to do here is save this out to a knowledge base with the rules on it. So I'm going to call this knowledge base automation and then hit save. The next thing I'm going to load is open up another part which has a whole bunch of these hole features in here. So I'm going to go ahead and load this part, which basically has 4 sets of the same part. Now I would like to program each of those holes. Now rather than having to program each of these holes individually, I have some sketches defined for this, which basically defines the holes for it. And I'm going to go over to the machining browser and then use this feature called load a knowledge base. And I'm going to go load the knowledge base which has the rules on it. And you'll now notice that the geometries are automatically being assigned based on the rules. So I didn't have to go through the process of selecting any of those machining features. They're automatically selected based on the rules that were put in. And you can now go ahead and run your simulation. So within just a couple of button clicks, you're able to effectively program your toolpaths by loading a knowledge base with rules. So this is one of the very nice features, powerful features, automation called knowledge-based automation, which is also available in all our configurations of VisualCAM nil for SolidWorks. Now with this, I would like to go ahead and turn this back to our VP of Sales, Anita, who can go ahead and get you more information about our VisualCAM 2016 for SolidWorks product. And if you have any questions, she'll be more than happy to answer them for you. Folks, thank you for your time.
Thanks, Uday. That was an information-packed webinar. Uh, uh, kind of just made it through. Thank you. Thank you very much. Thank you, folks, for joining us this morning. It's been a very busy morning with a lot of information thrown at you. So we did get to some of the questions that were posted in the chat session during the webinar, but not all of them. I would definitely encourage you to either call us, give us either through chat or phones or an email to any of us at MecSoft. We will be glad to talk to you about VisualCAM 2016 for SolidWorks. Great new features for the new users. We'd be glad to run a one-on-one demo if required. So do contact us. Again, thank you very much for attending. This webinar has been recorded. We will send out an email as soon as it is uploaded for viewing. And like I mentioned earlier, feel free to contact us, call us, email us, Skype us, chat with us, and we will definitely look forward to hearing back from you. Thank you, folks.